Hey everyone, and welcome to this explainer on EPA Method 5A. We're going to jump right in and dive into the precise, chronological journey of measuring particulate matter, specifically in the asphalt industry. If you work in environmental compliance or source testing, you already know that capturing accurate emissions data is an absolute must, right? But it isn't always straightforward. So today, we're unpacking exactly how the EPA mandates we handle one of the absolute stickiest, most complex emission sources out there, asphalt processing. By the end of this, you're going to have a crystal clear, full overview of the rules, the specialized gear, and the math that makes Method 5A tick. Let's get into it. Here's a quick look at our roadmap for today's explainer. We'll start with a full overview of Method 5A, look at the specific equipment and reagents, and then walk right through the sampling procedure. After that, we'll take a really quick QSTI exam prep break, followed by sample recovery and analysis, and finally, we'll wrap up by calculating those final PM emissions. All right, Section 1, Method 5A, full overview. Let's dive in and see exactly what sets this procedure apart from the rest of the EPA's catalog. So unlike your standard tests, Method 5A is really tailor-made to handle the uniquely sticky challenge of asphalt process emissions. When we talk about asphalt roofing saturators or blowing stills, we're dealing with intensely high temperatures and complex organic compounds that behave very differently from typical particulate matter. The EPA recognized pretty quickly that a one-size-fits-all approach just wouldn't work here. If you use a standard test, you may completely miss the material that condenses at specific temperatures, or worse, you could absolutely ruin your equipment with asphalt residue. This method guarantees that the PM mass, which crucially includes any material that condenses at or above the filtration temperature, is captured accurately. Here's the crucial point. While this builds on the foundation of Standard Method 5, the deltas, meaning the exceptions or differences, are what truly matter for accurate asphalt testing. You absolutely need a thorough knowledge of Method 5 to even attempt 5A, but you can't simply swap them out. Method 5A introduces some incredibly strict mandates on heating systems, specific solvent usage, and uniquely designed glassware. This is all to ensure those heavy, unforgiving tar-like particulates don't escape measurement or completely gum up your data. Moving right along to Section 2, specific equipment and reagents. What's super interesting here is the highly specialized gear you actually need to pull this off. 42. This number is absolutely critical. We're talking 42 plus or minus 10 degrees Celsius, which is about 108 degrees Fahrenheit. That is the strict temperature you have to maintain for the glass fiber filter and the pre-collector cyclone. If the stack gas temperature is running extremely hot, let's say over 250 degrees Celsius, you might actually need to deploy water-cooled probes just to bring the temperature down to this precise 40-degree window before it even hits the filter. And why go through all that trouble? Because the EPA wants to capture the specific fraction of asphalt material that condenses at this exact thermal threshold. And to clean up that 42-degree particulate, you need the right chemicals. You have to use TCE. That's 1,1,1-trichloroethane, instead of the standard acetone used in other methods. Acetone just won't cut it for dissolving asphalt. But here's the kicker. You actually have to run TCE blanks before field use to ensure the residue in the solvent itself is incredibly low. The standard demands reagent-grade TCE with less than or equal to 0.001% residue. You're also required to use stopcock grease that is specifically TCE insoluble. You've got to be incredibly careful here. If you use the wrong grease, your solvent is going to dissolve it right into your sample and completely ruin your gravimetric weeds. It's a super common rookie mistake out in the field, and it will literally cost you the entire run. All right, Section 3, the sampling procedure. Let's head out to the stack and see how we operate this precision, temperature-controlled vacuum system. Okay, before you even think about turning on those vacuum pumps, you have to check your stack gas moisture. If your stack gas is excessively wet, meaning it's over 10% moisture, you have to add a borosilicate glass pre-collector cyclone into your sampling train, right between the probe and the filter holder. And remember, that cyclone also has to be maintained at our magic number of 42 degrees Celsius. But if the moisture is under 10%, the EPA explicitly states you shall not use it. It's a strict binary rule you've got to follow during setup. Once you're all set up, the actual run begins. First up, your prep involves thoroughly cleaning those probe liners with soap, water, and a minimum of 3 TCE rinses. Then, you start pulling the gas. Think of this process like an extreme balancing act up on a loud, vibrating smokestack. You're constantly tweaking flow rates to maintain perfect isokinetic withdrawal speed, which just means the gas entering your nozzle is moving at the exact same velocity as the gas in the stack. And while you're doing that, you're simultaneously fighting to regulate that filter exit temperature against whatever the ambient weather is doing. It requires constant dynamic adjustments throughout the entire test run just to stay within the EPA's really tight operational parameters. Section 4, QSTI Exam Prep Break. As we pack up our gear to head back to the lab, let's take a quick breather for those of you aiming for your professional certification. Navigating complex methods like 5A can honestly be incredibly daunting, especially if you are studying to become a qualified source testing individual. But you don't have to do it alone. If you want to pass your QSTI exam, please subscribe to this channel and send us an email right now. We are totally dedicated to providing expert study resources that break down these complex EPA methods so you can step into that exam room with absolute confidence. Okay, Section 5, Sample Recovery and Analysis. We're back in the lab, so let's break down exactly how we meticulously recover the particulate matter we just captured. This 3-container protocol? It's your bread and butter. It ensures absolutely no PM or condensed moisture is lost during the transfer. Container 1 holds your delicate glass fiber filter, which has to be desiccated for a full 24 hours to remove uncombined water before you weigh it to a constant weight. Container 2 is your wash container. You're going to use TCE to carefully rinse the probe nozzle, the liner, the pre-collector cyclone if you used one, and the front half of the filter holder. Finally, container 3 is your silica gel, which is simply a way to figure out how much moisture you pulled from the stack. Now, this specific rule brilliantly illustrates the strict boundaries the EPA puts on you during analysis. When you evaporate that TCE wash to find the weight of the particulate left behind, you are allowed to subtract the weight of the residue that was naturally present in the TCE solvent itself. However, you can't just subtract massive blank values to magically make your emission data look better. The EPA strictly caps this blank subtraction at 0.001% of the weight of the TCE used. It's a great, built-in safeguard for data integrity. And finally, Section 6, Calculating Final PM Emissions. Let's slow down and translate our recovered physical samples into the hard, regulatory data that facilities actually use to prove compliance. First up, we calculate the moisture content using equation 5A-2. Now, what's totally crucial to remember here, and the EPA is very specific about this, is that if you're dealing with saturated gas streams or streams with water droplets, you actually have to do 2 calculations. You calculate moisture based on the water you physically collected in your impingers and silica gel, and then you do a second calculation assuming 100% saturated conditions based on the stack temperature. You must use the lower of these 2 values as your correct moisture content. Why? To avoid overestimating the moisture from liquid water droplets, which would skew your final dry gas volume calculations and completely throw off your results. Next, we figure out our TCE blank concentration using equation 5A-3. This just involves dividing the mass of the residue from your blank sample by the volume and density of the TCE used. You do this calculation to ensure you know exactly how much background weight you're legally allowed to subtract from your final particulate catch, always keeping in mind that strict 0.001% ceiling we just talked about. And we've reached the finish line with equation 5A-5. Here, we calculate the total particulate matter concentration. You do this by taking your total PM weight, which is just the sum of the weights from your filter and your TCE wash, minus that allowable blank, and dividing it by your total dry gas volume collected during the test. This gives you the actual concentration of asphalt particulate matter entering the atmosphere, which is the final bottom line number regulators are looking for.
Well, we've covered a ton of ground today, right? Everything from 42-degree temperature constraints to TCE wash limitations. But looking at these incredibly specific legacy methodologies leaves you wondering how environmental compliance is going to continue to shift as industry tech advances. As asphalt plants adopt cleaner, more efficient heating and capture technologies, are these highly specific legacy testing methods going to need a complete overhaul or just another delta? It's a fascinating question for the future of our industry. Thanks so much for joining this explainer, and we will catch you on the next one.